Well, hello everybody, and welcome. Where do I start?
You can ask about the audience, like how many are app developers for Android?
It's
So 50%.
yeah, 50%. Excellent. We are Zoran and Mårten, and we come from Sony Mobile Communications, located just north of here in Lund. And we've been working on Android since basically the beginning of time, since Android's been made public. And today we would like to talk to you a little bit about Android framework and application resources. The resources API that's been public in Android since basically before Big Bang, since before it's been made public. So it's actually really interesting that a topic like this would be featured in a diverse conference like this, because there's some, gory details of internals of Android. Among those of you who are application developers, how many of you have looked into our class, fiddled with it, or at least stared at it to make sense of those weird hex numbers? That's kind of not a nice experience that you would like to talk about. No. Any platform developers here, system developers? I think I see at least one, perhaps. Yeah, two, three. Yeah. So sometimes you have to rebuild framework because resources get twisted somewhere somehow. True story. And we're going to touch upon these mysteries of life in this talk. So let's just jump right into what resources really are, and then we will attack the acronyms.
Exactly. So let's start with the easy part, the no acronym thing, resources. So resources, as we all know, they come in different shapes and forms. There's simple stuff like integers and booleans, somewhat more advanced stuff like strings, and the really complex resource types like drawables and XML. In fact, out there in the wild, we've seen examples of games storing their levels as raw resources. So basically, resources can be used for whatever you like. On a high level, this is how you interact with resources. You call one of the get methods on a resources object. The system performs some magic and returns you a suitable value. So my job today is to explain to you what goes on inside the magic cloud. But to do that, we first need to establish some of the basic building blocks of resources. So let's start with your APK file. An APK is simply a zip file. There's the compiled bytecode, the manifest, some metadata like security and versioning, and for our purposes, most important, the resources. The files on the rest may not surprise you, but what is that resources ARSC file? Resources ARSC is the index of all resources in your APK. Resources ARSC is also pretty hard to pronounce, and the extension RS is way too similar to what I'm not really supposed to say on stage, so I'll just refer to this file as the resource blob from now on. The resource blob is a hash map on steroids. It is highly optimized for efficient lookup in runtime. And it achieves this because, as you can see, it's a binary format. It is created with the correct NDNS of most embedded devices. And it is stored as an uncompressed file in the APK zip file. And this allows Android to simply memory map the file without first extracting it. The actual grammar of the resource blob falls outside the scope of this talk, but if you're interested in that, come see a shrink or us later, and we'll happily explain the format for you. So let's move on to the how the resource blob is created. The creation is the job of the AAPT tool, the Android Asset Packaging tool. This command is the command you always run when first creating your application. So here, AAPT will convert your XML files into binary format for faster lookup on device. And it will also scan your resource directory, creating the resource blob we just talked about, as well as the R.java file, the one with the mystical hex numbers. Note, by the way, how you pass in the resource directory to apt using the S flag. So apt doesn't really care what the name of your resource directory is, but as we all know, res is the de facto standard. This is what your APK looks like after apt is done. So note that we're still missing the compiled bytecode and the security stuff. Later stages in the build chain will add those. apt is only concerned about resources. Now, apt creates all this in a single go. And the downside to that is that you waste time recalculating the same values over and over again when rebuilding your application, even if you haven't changed any resources. The solution to that problem is AAPT2. So this tool will create the same artifacts as its predecessor, but it works much more like a traditional build system with individual compilation steps and a final link step. And as a matter of fact, AAPT2 became the default tool just 2 weeks ago with the release of Android 3.0.
Android Studio 3.0.
Android Studio 3.0. So you can use both AAPT and AAPT2 for things other than building. So for instance, you can use it to inspect the resources in an already compiled APK file. So using the dump resources command, you will see all resources available. You can also run the dump badging command to see some metadata about your application. And you can use the dump badger command to display an ASCII art badger. Let me zoom that out for you. This is the one reason you would stick with AAPT1, because AAPT doesn't have this feature yet. So let's move on to that mysterious R class. For every resource type, there is a corresponding inner class. Within each class, every resource of the given type is enumerated with a unique numerical qualifier. Now, I'll talk about these numerical qualifiers for a bit and the actual number values. But when coding, always think of these numbers as completely random, because anytime you recompile your application, if you've changed any of the resources, these values will actually change. But that raises a question, doesn't it? Like, how come the SDK that builds the framework, how come the SDK is backwards compatible? Well, the reason is that the SDK and the framework contains a file called public XML, and the public XML file maps all the public resource types and names to their numerical qualifiers, thus ensuring that AAPT can reuse the previous values. So, of course, any of the private resources in the SDK can and will change between compilations. So, as always, never rely on something in the SDK that isn't explicitly marked as public. I'm sure no app developers have ever done that.
Which is why I mentioned the rebuild of framework, for example. That's why it happened.
Yeah, we can share some horror stories about changing these values if you find us afterwards. We have quite a few, I think. So a resource numerical qualifier consists of 3 parts. The highest bits tell us which type of package we're looking at. So 7F is the most commonly used value since it's used by regular applications. But there's also 01 for the Android framework and 00 for shared resource libraries. The next few bits tell us which type of resource we're dealing with. So that would indicate if it's an integer or a Boolean or anything like that. There is no fixed mapping between resource types and their numerical values. But within the same package, every resource of the same type will have the same type identifier. And finally, there's the entry number, and this is just a running number. So reading this example from right to left, we're looking at the second resource of type 5, whatever the 5 means, in a regular application. So far, we've focused on how the R class maps resource types and names to their numerical identifiers. And of course, during development, we tend to think of resource types and names, and in runtime, Android uses the numerical qualifiers for faster lookup. Either way you think of it, these are keys in a dictionary. And in its simplest case, resources are a one-to-one mapping. But it can be a one-to-many mapping. And this is the real beauty of resources. The same key can map to different values based on parameters outside your running application. I'm sure you're familiar with how you can provide translations for different languages or layouts for different orientations. And you do so by placing the resource values in folders with special suffixes, like values SV for Swedish. These parameters are called qualifiers, and a set of qualifiers is called a configuration. Normally, you would only use, say, 1 or 2 qualifiers, but nothing prevents you from using all the available qualifiers, and there are a lot of them. On this device running Oreo, there are 22 qualifiers, and more are added as Android continues to evolve. So, for instance, in Oreo, the wide color Gamut qualifier was added. Think of it as a many-dimensional matrix, and your mind will just explode. So stick to 1 or 2 qualifiers if you can.
Yeah, just the other day I found out about the version qualifier. That was a revelation for me, like after 7 years working with this, and it's like, well, version.
We're all human.
Lovely. Yeah, we're all human, obviously.
Right, so remember this. We're finally ready to deep dive into the magic part. Again, first you call one of the get methods on a resources object. Whichever method you call, it's eventually going to be forwarded to the internal method getResourceValue. And this, by the way, is where you leave the Java world and enter native code. So every resource lookup comes at the cost of a JNI call. Your application process not only loads its application APK, but it also loads the system APK, as well as potentially some other APKs. So at this point, the lookup code comes to a fork in the road. In which of the APK files should it continue to look for the resource you're looking for? Well, the answer lies in the highest bits of the resource numerical identifier. In this case, it's 7F, so we continue with the application package. In this example, the resource we're looking for is defined in 4 different versions. So let's zoom in on those. The framework will return to you what it considers is the best match given a requested configuration. Normally, the requested configuration simply corresponds to the device's current configuration. And in this example, the requested configuration is something something Swedish portrait. Now, the framework will go through its list of versions of a resource while looking for that best match. And it will keep track of the best match found so far. And for every version, there's a check to see if it's compatible with the requested configuration. And if it is, there's an additional check to see if it's a better match than the one we've found so far. So let's start from the top. The first version is defined for the default configuration. And by definition, default is compatible with every configuration. And since we didn't have a best match already, this becomes the best match. Then we move on to Danish. And personally, being Swedish with family in Denmark, especially here at Øredev, I think many agree, I tend to think of Danish as compatible with Swedish, but that's not the opinion of the Android framework, so Danish is skipped. Next up is Swedish. Now, Swedish is compatible with the requested configuration, so this now takes over as the best match. Exactly what makes one version a better match than another is something you actually have to look at the source code to find out. But as a rule of thumb, the more qualifiers, the better. Finally, we come to Swedish landscape, but because landscape is not compatible with portrait, this version is skipped. So in the end, the best match turned out to be Swedish, and that's the value returned to your application. So let's go back to that binary file, the resource blob. In the resource blob, the resource values are encoded using this structure. The data type tells us which type of resource we're dealing with, and the data field encodes its value. So for simple resource types like integers or booleans, the 4 bytes in data are enough to encode the entire value. But if we're looking at a string, the data field is an integer offset into another part of the resource blob where strings are stored. So that's one additional lookup for the framework before it can return your value. And in the hairiest case, where the data type is drawable or an XML, the contents of the resource value is actually stored as a file outside the resource blob as a separate entity in your APK zip file. In this case, data is again an integer offset to a string, and the string's value is the path within the APK where the additional contents file is. So that's 2 additional lookups for the framework. Remember how we told AAPT to look for resources using the S flag? Well, you can actually pass in several S flags to AAPT, in which case you get sort of a union of the resource directories, where some directories will provide basically a diff of resources, in essence patching the other directories. And this can be really handy if, for instance, you want to, I don't know, provide different resource types and values for a debug build, or if you're a platform modder and you want to modify some of the core applications without touching their source code. This is called static overlay, and sometimes static overlay is just the ticket for your problem. But because everything happens in build time, sometimes static overlay simply isn't enough, is it?
Yeah, that's for sure. Modularization seems to be one of the hot topics nowadays with all TensorFlow and Kotlin, all with the splits that allow you to build different versions of the APK depending on supported density or ABI, or shared libraries like Android Archives that are sort of like JAWS but with Android Spice that allow you to add manifest and resources to your libraries. But we will not talk about them here today. They do deserve their own talks, and in fact you can watch a lot of them online. Please make sure to do so. Instead, we're going to talk about something somewhat similar. Now, in the role of a stereotypical device manufacturer, we just had to modify a value in framework. And compile time customization was prohibitively expensive. We needed to reach many customers, but not all of them. And we needed to minimize time spent in the factory. Of course, our implementation had a bug. What was the estimated time fix for a bug fix?
I seem to recall that I needed 3 weeks for that.
3 weeks. So 7 years later, here we are. And the bug was fixed in 3 weeks, so Mårten was spot on. But we found that the solution is applicable to many more use cases, and it eventually evolved into something we now call a runtime resource overlay, acronym CHECK. It's been part of Android open source project since 2010, and we've been contributing continuously in several iterations. In fact, we have ongoing patches in AOSP Garrett as we speak. But what is runtime resource overlay? It's a way to overlay, that is, extend or modify resources of framework or application in runtime, that is, post-build while running a device and without reboot or unnecessary interruptions that could cause ANRs or janks. But why would you want this? Well, software customization is basically bread and butter for device manufacturer, and amongst other things, it's a way to deploy software using one build with multiple configurations, where runtime resource overlay would typically be a configuration for a given carrier, network, or region. For example, you would configure your device to work properly in a given network so that you can actually make a phone call. Or you would configure an application so that you comply to regional laws. Then there are personalized themes, and you've probably seen them in some of your favorite devices or mods. It's basically a way for you as an end user to play dress up with the software of your phone, together but not the same, right? So they would typically modify a color value or a graphical artifact, which are usually defined as resources. Having these use cases in mind and the origin of the idea, starting to develop this, we set up some design goals up front. First off, the whole process should be transparent. There will be no changes to the existing APIs, so the applications would just continue working as they were. And development process would be intact, so if you, as a developer, if you don't want to use runtime resource overlays, you don't have to. You don't even have to know that they exist. But if you do, the entry bar should be really low. And for end user, like I said, there will be no reboots and there will be no unnecessary interruptions that could cause ANRs or even janks. For that, everything needs to be really fast. So load and lookup of resource overlays would have no noticeable difference from load and lookup of regular resources. And we really looked up to the resource blob, how it allowed for almost direct access to resources. And we really wanted that for resource overlays. But to do that, everything needs to be really secure. So we wanted to be able to reuse an Android security model with permissions and signatures, the whole shebang. Since we're adding resources, for modification, low memory footprint is really important. So no big databases, no markup files, XMLs, none of that. So it really appealed to us how resource blob is compact and how efficiently it can be memory mapped. Which is why early on we decided that the physical representation of a runtime resource overlay should be an APK. Just a regular package that package manager knows about and all the rules of package management apply. So if you were to unzip such an APK to list its contents, you would notice that it contains all the building blocks of an APK except the code. It contains a manifest, metadata with signature, and resources. Now, these resources are specifically picked by the type and name from the original, let's call it target package, whose resources you want to modify. And you only need to add those resources that you want modified. You don't need all of them, so it's like a sort of a diff. Note how there is no R.java file, there's no R class there's no dex, none of that. You really don't need numerical identifiers present within the overlay project for everything to just work, and you can use whatever build chain you're used to. And I will get to that later. So you take the resources that you want to use for modification and you add a manifest next to it. Now this is like a regular application manifest that everybody's used to, right? So it has package name, it has version info, etc., etc. The most important element of this manifest that you would not find in a regular manifest is this overlay element that practically defines the overlay package. And the value of its target package attribute is, of course, the package name of framework or an application whose resources you want modified. We used to have another attribute in this element called priority that basically told the system the order in which you want overlay packages to be loaded in, but we'll tell you later how and why that was deprecated. But so like I said, you can put the resources that you want to use for modification in a folder, you put the manifest there, and then whatever build chain you want to use for building this. And let's say you've built an APK like this and you placed it somehow on device. So how does lookup work? And doesn't this slide look familiar? That's because existing APIs did not change. So you continue to acquire resources the way you used to. You would call an appropriate getter from resources object using the type and name of the resource defined in the R class. So consider it a bit of an API there, like type and name of that resource. It would invoke the native call to get resource value with appropriate numerical identifier defined in the R class. Now, the system would load one or more overlay packages in appropriate place, so with the appropriate target package, thanks to the overlay element of the manifest in the overlay package. And let's say in this example, we continue on the example from the previous section where we had 4 drawable droid resources defined in different versions, and we add 2 overlay packages with 1 resource each. Eventually, the best match will be returned. Let's zoom into that. And let's say that in the example you're like me and you always have your device set to English locale. You're looking at a page in portrait mode. So what happens with resources? Of course, the default resource is the first and foremost candidate for the best match. And it's a better match than Danish or Swedish landscape. However, the default resource defined in the overlay package wins over as the best match. That is because with the same qualifiers, the resource defined in the overlay package will always win over the resource defined in the target package. And remember how Mårten said, more qualifiers the better. There's a pitfall there. So with appropriate qualifiers, the resource defined in the target package can still win as a best match. So someone in this conference would have Danish as their locale, and the Danish resource in that case would win as the best match. Now, you will notice that we added overlay packages on top of the target packages resources, and then the snarky part of Rune goes, performance. Everything is really fast. So if the overlay package doesn't define the resource that you're looking for, it's just skipped in lookup. And then the resources have this sort of direct access and really nice jumps through offsets thanks to the resource blob and thanks to the numerical identifiers. So, okay, we got to this point. How do we build overlay packages without numerical identifiers present, and how does the system know which numerical identifier to associate to the resources in overlay packages? We thought of that, and we built a tool that runs on device. We called it the ID map tool. It creates a one-to-one mapping between the overlay package and the target package. That is between the type and name of a resource in the overlay package and the numerical identifier defined in its target package. Now, the neat thing about resource blobs of frameworks and application is that they contain all the information about resources, everything. So IDMap can actually use this to perform a reverse lookup using type and name of resources, figure out their numerical identifiers, and record this mapping on device in a binary file that we so creatively named IDMap file. Now, this is a sample dump of such a file. And note how you can send commands to IDMap tool. In this case, inspect, that is pre-print or dump the IDMap file. The IDMap file will have a header where you will have the physical path to the overlay package, to the target package, that is. You will have the data header that will tell what kind of type of the package that is. Remember from the example 7F for applications. And the data block will actually contain the information about the resource, its type, name, and the running number that it then can construct the numerical identifier out of. For more information, don't hesitate to ask questions. I'll stop here. Now, runtime resource overlay has to be preloaded in a specific path on device and can only be preloaded to this specific path by platform developers, by device manufacturers and modders. Both of these for security reasons, basically. And up until Oreo, they were automatically loaded by the system just by virtue of being in that specified path. But that somehow wasn't enough now, was it?
Of course it wasn't. So the use cases we've talked about so far, the customization of the device and theming, both these use cases really require access to a system that's much more dynamic than something that depends on what you preloaded on the file system. We really needed a system that allowed us to selectively reorder or use or not use some of the overlay packages present on device. And the solution we came up with was to introduce a new system component. And this component we chose to call the Overlay Manager Service, or OMS for short. So that's the second abbreviation, check. Now, a quick sidebar about how the Android framework is structured internally. It consists of several modules called system services. And the naming can be a bit confusing if you have a background in application programming, because a system service is quite unlike the service class you use as an app developer. A system service doesn't have a lifecycle. It's always running, and it's started in a hard-coded order during boot of Android. Whenever you interface a manager in your application code, that manager is usually backed up by a corresponding system service. So for instance, if you call the package manager, your calls are eventually routed to the package manager service. This link between the application and the system is implemented as an AIDL interface. And the dotted line in the graphics indicates that we're moving from one process to another. So again, an AIDL interface. This is the AIDL interface for the overlay manager service. It contains a few methods to reorder the overlays. And this, of course, as Ron mentioned, has implications if you have two overlays targeting the same package and modifying the same resource. And this is also what deprecated the hard-coded manifest attribute that Zoran mentioned. There are also a few methods, the set-enabled methods, that toggle if an overlay should be used in the first place. All these methods cause a ripple effect in the system, forcing the framework or the applications, depending upon what is actually affected, to reload its resources. Then we have a few methods to query the current status of the overlays. And these all return a new class called overlay info, or at least a collection of overlay infos. AIDL, the language you specify these interfaces in, doesn't allow you to specify a type on the containers, but both the map and the list are actually using overlay infos as their generic type. So because overlays are regular packages, you would ask the package manager about most information about them, but overlay-specific information is contained in these overlay info objects. And the most important part of an overlay info is the overlay's state. So an overlay can be enabled, meaning it's loaded, or disabled, meaning it's not loaded, but it could be, or it could be in one of the error states that prevent it from being loaded. So for instance, maybe its target package isn't even installed. Runtime resource overlay relies on the security inherent in the resource lookup system, but adding a new Java interface brought in a new attack vector. And without security measures in place, a malicious overlay could, I don't know, crash your device or change the customization, or, which happens to be my favorite, simply swap the yes and no text in a dialog box.
That's not my favorite.
So hardening AIDL interfaces on Android is usually done by checking the caller's permissions or signature. And for the overlay manager, we reused an existing permission for the read operations and added a new one for the write operations. Now, I should mention that these permissions are all protected with signature or privilege permission, which in essence means that unless the vendor that put together your device has approved of your application, you can't have these permissions. So what does interacting with the overlay manager actually look like on a running device? In the video clip I'm about to show you, we're using a Sony Xperia X device running the Open Devices program, which in essence means it's running a USB Oreo. So on the left, there's a screen grab of my device, and on the right, I'm using the ADB terminal to communicate with it. I've started my demo application, and I just enabled an overlay targeting that demo application. So you saw the graphic change from regular green to blue. Now I'm going to enable an overlay targeting the entire system. And notice how the colors change not only in settings, but in settings UI as well. So this is a framework overlay. This overlay also highlights that neither me nor Zoran knows anything about graphics. So let's turn that overlay off again. And finally, let's move back to the demo application and disable that overlay. And we're back to the vanilla resources.
So we have a device there with this demo, so you can check it out if you want afterwards.
Yep, don't hesitate to approach us. We won't bite. So what actually happened when we enabled an overlay? Well, first a client sent a command to the overlay manager. And in the demo, we used the ADB shell to do that, but it could be anything with access to the AIDL interface. So for instance, a theme picker application. If the overlay manager accepts the request based on the permissions and all that, it will then tell the package manager about the change in APK paths. Any application started after this point will be correctly set up. But the overlay manager also needs to worry about any currently running applications. And for that, it asks the activity manager for help. The activity manager will go through its list of running processes, and for any application or framework affected by the change, will send that process a message. Before I continue with that, let's have a look at how your application code interacts with resources. From your application code, you only access the resources object. But resources is actually just a dummy class forwarding all your calls to an underlying resources implementation. And the implementation is what really loads your resource blobs. Both the resources and its implementation are orchestrated by the resources manager. Because your application code only knows about the resources object, the manager can swap out the underlying implementation at any given time. So keep that in mind for the next step. Let's go back to the message from the activity manager. The message is picked up on your application main thread. And this triggers the resources manager to create a new set of resource implementation objects and to load the new resources. The manager will then redirect your resources object. And finally, your application will perform a on-configuration change. And this ensures that your new resources are in use. And that, in a nutshell, is how the overlay manager service works.
So, there you had an opportunity to hear what resources are under the hood, how they really work, and I hope we answered some of those life mysteries of resources. You found out how you can extend the resource pool using Runtime Resource Overlay, and how you can access that functionality through a Java interface using OMS. And OMS is in Oreo today, so it can be used. The API itself is not public in the SDK, so platform developers can really enjoy that part of the functionality as well. Everybody can, though, use all the tools that we mentioned here. So APT, APT2, overlay service ID map, all that can be used for debugging, for building, for whatever you want. Besides that, you would probably ask yourself, okay, what's in it for me with this? Well, for platform developers, the answer is kind of obvious. So if you were to configure your device with either a parameter customization or a theme, so with graphical artifacts and that, this technology makes your life so much easier. If you're an application developer, the answer is not so obvious. So let me start with one thing. Don't try to outsmart the system. By saying that, I mean don't try to optimize where you don't need to optimize. So if you want to acquire a resource, use getResources API. Don't cache the resource in a variable or, God forbid, shared preferences. Nobody uses shared preferences for that, right? Excellent. So don't do that. Next thing to understand is that your platform might as well use this. So, for example, someone will put a theme on the system UI, and all of a sudden, the system styles that you combined with a resource that you defined in your own application doesn't work. Like blue text on blue background really doesn't read well. So don't mix and match. If you're using system resources, use system resources. Don't define your own resources that kind of redefine the resources that you can actually get from the system. So don't do that either. Just work with the system, not against it. Also, bear in mind that your resources are also basically an API, and that's probably one of the key takeaways from this talk is that your resources are APIs. Somewhere down the line, you might want to do something different with those resources, and then you will want to keep consistency like you would for the APIs. And if AOSP commits are any indication of future to come, it will be possible for you as an application developer to also overlay the resources of your application. So be cognizant of that you might end up on a platform with an older version of your application where you will want to reconfigure that application to work better on a new platform just by using the resources, which is why start thinking about resources as APIs. just have that mindset. There's many things to add to this, but if any of you is inclined towards visual arts, you could perhaps use a tool such as Theme Creator to build overlay packages to theme your devices. That's always fun. And with that, let's close this talk. Thank you all for listening. If you have any questions, please don't hesitate to ask. And yeah, thank you.
Thank you.